Hello, my name is Jeff Messier. I'm a professor in electrical and software engineering in the Schulich School of Engineering. And in this lecture, I'm going to talk about memory, how memory is organized, and basically how we organize the values that are stored in memory. Before we get into that, I just want to review a few things about number notation. And in this module and in this course in general, we're going to use several different number systems. We're going to use base 10 numbers, we're going to use hexadecimal numbers, and we're going to use binary numbers. And just to be, I guess, just to start with the most familiar, base 10 numbers are what we've been using all the way through elementary school. This is our standard numbering system. And for example, if I were to write the number 3,821, for the purposes of this slide and this discussion, I'm going to give a subscript 10 here, and that is going to indicate that this is a base 10 number. And the value of this number can be calculated by multiplying each of these digits by a power of 10. So 3,821 is equal to 3 times 10 to the 3 plus 8 times 10 to the 2 plus 2 times 10 to the 1 plus 1 times 10 to the 0. And the powers of 10 are a function of the position of each one of these digits. Binary numbers are base 2 numbers. And so if I were to write out 1101, I could, just to indicate the base, write a little subscript 2 to indicate that we're using a base 2 number. And just like our example for the 10 base number, the value of this binary number is 1 times 2 to the 3 plus 1 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0. Or in other words, if we add up all of these numbers, this is 8 plus 4 plus 0 plus 1, or 13 if we want to write it in terms of base 10. Now, when we're working with binary numbers, we're going to be grouping them together. A byte is equal to an 8-bit base 2 number, and a nibble is a 4-bit base 2 number. 2 nibbles make a byte, obviously. Another really common number system that we're going to be using in this class are hexadecimal numbers, which are actually base 16. Now, base 16 seems like a strange number base to use, but the numbers 0 through 15 are the maximum range of numbers you can represent with 4 bits. And so computer engineers like to use hexadecimal numbers because it's relatively easy, once you get the hang of it, to very quickly translate between hex numbers and binary numbers. A lot easier than it is to translate between base 10 numbers and binary numbers. And for hex numbers, since we've got 16 values that we represent using digits, we start with 0, 1, all the way up to 9, and then we use letters after that. We go A, B, all the way up to F. And so if we go, if we add A through F at the end of 0 to 9, we get 16 values. And so if I was to write out a hexadecimal number, it would be a mixture of, or it can be a mixture of letters and numbers. And so for example, A2 F9 is equal to A, which is actually 10, right? Because it goes 0 through 9, and then A represents 10, B represents 11, F represents 15. So this hex number is equal to 10 times 16 to the 3. I'm just going to move my example here so we don't get so cluttered. Plus 2 times 16 squared plus F, which represents 15. 15 times 16 to the 1 plus 9 times 16 to the 0. And if you do all of this math and express it as a base 10 number, it ends up being equal to 41,721. And that's fine, but again, really the reason why we like hex numbers is because it makes it very easy to translate between hex and binary. And so I'll just give myself a little more space here. I'll delete the base 10 example. Delete. So as I was saying, each hex number can be represented using 4 bits. And if you get good at it, you start to basically sort of remember how the 16 values map directly to binary. And so the number 10 can be represented as 1010 because that's 8 and that's 2, right? 8 plus 10, or 8 plus 2 is 10. The number 2 is represented as 0010. The number F is the maximum number, it's 15, so that's 1111. And then the number 9 is 1001, 8 plus 1, right? And so very quickly we can go from the hex number to its equivalent in binary. And so we're going to be heavily using binary numbers, hex numbers, base 10 numbers. I typically, when I'm using binary numbers, I typically won't put, base 2, I won't put base 16 for hex numbers. Most commonly when I'm using hex numbers, I will precede it with the prefix 0x. So if I write 0x12, that's not equal to 1 times 10 plus 2 times 1. Instead, that's equal to 1 times 16 plus 2 times 16 to the 0, right? So 0x represents a hex number. Sometimes I will use 0b to represent a binary number, but typically I won't, because in most of the examples when we're using binary, it'll be self-evident that we're using binary. Now, just a quick word about prefixes. So in general, most people are familiar with the standard metric prefixes. So for example, kilo means, oops, change my color here. So kilo means 1,000, mega means 1,000,000, giga means 1,000,000,000. And we use these prefixes a lot when talking about computers, right? We talk about a 250 gigabyte hard drive. Sometimes we talk about a 1 gigabit per second Ethernet link, talking about the throughput of the Ethernet link. But kind of confusingly, typically when we talk about storage, memory size, we're not using the standard base 10 definitions of kilo, mega, giga, tera. Instead, we're using the base 2 definitions. Now, these base 2 definitions, and I'm showing them over here, have their own words. So instead of talking about kilo, when we talk about a 1,000, the prefix that's roughly equivalent to 1,000 in base 2, we should be saying kibi. And kibi represents 2 to the 10, or in other words, 1024. So when we talk about but confusingly, most often, like when you look at computer vendor sites or when you talk to people, they'll still use the metric term, kilo. So when we talk about, oh, this is a 1 kilobyte, this memory can store 1 kilobyte of data, we're talking about a memory that can store 1024 bytes, not 1000 bytes. When we're talking about a 250 gigabyte hard drive, we're talking about a hard drive that can store 250 times 2 to the 30 bytes rather than 250 times 10 to the 9 bytes. Now, I'm trying to change, I guess, right? So, when I can, I will use the prefix ki, mi, gi. But really, this is not what's still typically done today. Like if you go onto a computer vendor site, you're buying, a solid state drive for your computer, they still will use the standard metric prefixes, even though it's understood that when you're talking about memory and you're talking about storage, the prefixes correspond to the base 2 definitions. And that's the convention that we're going to be using in this class. So whenever I talk about memory size, even if I, slip up and say kilobytes or megabytes, it's always the base 2 prefix definition. And when I talk about anything else, like if we were to talk about, the throughput or the data rate of, a digital link or something like that, then we'll use the regular metric definitions. So can be a little confusing. If you just remember, like it's always base 2 if we're talking about memory, then you'll be fine. And if you need clarification, obviously just ask. When working with memory, we talk about not only the contents of the memory, but also we talk a lot about addresses and memory addresses. And basically, when we think of memory as an array of bytes, the address of each byte is basically the index of that byte. And so if this is the first byte in our array, it has index 0, and we would say that this byte is at address 0. The second byte has index 1, and we would say that this byte has address 1. So this index column is basically the address column. And by convention, in this class, I will be drawing memory kind of from the bottom up. So address 0 will always be at the bottom of the memory diagram, and then as we go up, the address of the bytes will increase. And that's the convention that you'll see in most textbooks, most data sheets. The only time that you see it reversed is when you are working with things like debuggers or programming environments that give you a snapshot of memory on a real device. Generally, then they will show, let's say maybe a little bit of a screenshot of your memory content, and they might show you, bytes or hex numbers. And usually this is address 0, and then this will be, this byte is address 0. This would be the address 1, this would be address 2, and so on, and then it sort of wraps around. So when we get into using our simulator programs that give us a snapshot of data memory and some of our development environments, you'll see memory represented in this way. But for the purposes of our lecture discussions, we're always going to use this kind of bottom-up convention. The other way we can picture memory is as an array of words. Now, a word is basically a group of bytes. So memory space can be grouped into multi-byte chunks called words. And when representing memory as an array of words, typically I will have several bytes all in a row. And one of these rows represents a single word. So for example, the ARM processor uses 32-bit memory or 4-byte words. And so one of these rows represents one word of 32-bit ARM memory. Now, this is basically just the way I'm drawing the memory. You can still obviously think of 32-bit memory as just being an array of bytes still, where the first 4 bytes correspond to one word and the next 4 bytes correspond to the next word, but it's just a little bit more it's just a little bit easier to visualize when you draw it this way. Now, as soon as you have multi-byte words, you are presented with 2 different options for how to do your addressing. You can use word level addressing or you can use byte level addressing. Now, word level addressing is basically using the indices that, or basically using the word indices, right? So that means the first 4-byte row of memory will correspond to address 0. And if we move this up, the next row of memory corresponds to address 1. The third row of memory corresponds to address 2, and so on. However, other memories, ARM is an example of this, still uses byte level addressing even though we are working with 4-byte words. And so what that means is the address of each word corresponds to the byte index of the smallest byte in the word. And so this byte is byte 0, this is byte 1, this is byte 2, this is byte 3. This is byte 4, this is byte 5, 6, 7, this one is 8, and so on. And so the address of this first word, I'll just change my color here. The address of the first word corresponds to the byte index of the lowest, or corresponds to the lowest byte index in that word. The address of the next word is the lowest byte index in the second word. The address of the third word is the lowest byte index in the third word. And so as microarchitecture designers, how do we decide on the width of our words? Well, basically the width of the words typically determine how many bits are operated on in parallel by the processor. So if we have 32-bit words, generally that means we're feeding 32-bit numbers into our processor. And the wider the word, the more bits that are operated on by our processor at one time, basically the bigger the numbers we can represent, right? So wider words have more, can allow numbers with more range and resolution. The disadvantage of wider words is basically cost. The wider your words, the wider the buses on your computer chip have to be in order to transfer all of those bits in parallel. So a 32-bit word typically requires buses that consist of 32 parallel wires. 64-bit words would be 64 parallel wires, and so on. And of course, as at this particular time when I'm recording this video, most modern processors are 64 bits. And so if you buy a laptop, even your smartphone, typically those processors are 64 bits. And it's relatively rare to see 128 bits. And so the reason why we haven't gone to 128 bits is that there today aren't very many applications that require numbers that big or resolution. So a bigger number will allow you to store larger numbers, but will also give you more precision if you're using sort of a floating point number. And right now, 64 bits is enough to give us numbers as big as we need and as precise as we need. And that won't change until we get onto applications that require bigger numbers or more precision. Because right now we want to, we also want to keep an eye on cost. And so 64 bits is kind of that sweet spot between number size and expense. So as soon as we have multiple bytes in a memory word, we have to talk about how we're going to index the bytes within each one of those words. And as it turns out, historically, there were two ways to do this, and they were the Big Endian byte ordering convention and the Little Endian byte ordering convention. And the terminology is actually from the book Gulliver's Travels. So in Gulliver's Travels, the king requires all of his subjects to open their hard-boiled eggs on the little end. And so that's not a very good egg, but if you were a little Endian, you had to open your egg on the little end. The Big Endians were the rebellious subjects that decided to open their eggs on the big end. And so that's where the Endian terminology comes from. The Big Endian and Little Endian conventions were basically used by different processor companies. Now, processor design companies. But now, before I go into explaining the difference between Big Endian and Little Endian, I should say that the convention that we use for ordering bits within a byte is always the same, regardless of which Endian convention you use. So if we look within a byte, we have, of course, 8 bits. And the leftmost bit is called the most significant bit, because this bit value, when we convert it to a 10-base number, is multiplied by 2 to the 7, or 128. The rightmost bit is called the least significant bit, because when we convert the byte into a 10-base number, the value of the least significant bit contributes only 0 or 1, whereas the most significant bit contributes either 0 or 128 to the value of the number. So for the Big Endian convention, we would use byte indexing for each of our words. And so that means the word address for the first byte is 0. The word address for the second byte is 4. The word address for the third byte is 8. And the indexing for the bytes within each word goes left to right. And so this is byte 0, byte 1, byte 2, and byte 3. And so for the bytes that I've circled, this first byte is word address 4, right there, and byte offset 2. The byte that I've circled up here is word offset 8 and byte offset 0. As you can imagine, Little Endian is just the opposite way. So with this Little Endian example, we still use byte level word addresses. So the first word has word address 0, the second word has address 4, the third word has address 8. But the byte ordering goes right to left. So this is byte offset 0, 1, 2, and 3. So this byte circled right here is word address 8, byte offset 0. The second address is would be word address 4, byte offset 2. Now, as I've noted in my slides, the Big Endian convention was used primarily for primarily by Motorola for their PowerPC processor, which was an important processor in the late 80s, certainly in the mid 90s. And then Little Endian convention was mainly used by the Intel processors. But over time, as Motorola dropped its PowerPC product, the sort of the champion for the big Endian convention kind of disappeared. And so now all major architectures today use the Little Endian convention. So the x86 processors, the ARM core processors, MIPS processors, all use the Little Endian convention. And so going forward, Little Endian is what we're going to be using in this course. So we've talked about memory organization, memory addressing in a very general way. We've talked about byte level addressing, word level addressing, words that can be a variable number of bytes. We've talked about big Endian, little Endian. Now I would like to conclude with two real world processor examples. And these are the two processors that we're really going to be talking about most in this course. The first thing I want to talk about is how an ARM processor organizes its memory. We're not going to be doing any hands-on exercises with ARM processors in this class, but I'm going to be using ARM as an example of a more sophisticated processor than the AVR. And as it turns out, ARM processors, modern ARM processors anyways, default to Little Endian, but they do actually support big Endian byte indexing as well. And depending on the version of processor, they use either 32 or 64-bit words. In most of our examples, I'm going to be assuming 32-bit words. And they use, as I said, byte level addressing. So if I was to draw a picture of ARM memory, it would look like this. So we've got 32-bit or 4-byte words. So each row of memory consists of 4 bytes. By default, we use Little Endian byte addressing. So the least significant byte is byte 0. And then we proceed all the way up to byte offset 3. And because we use byte level addressing, the address of the first word is 0. Address of the second word is 4, 8, and so on. The AVR processor is interesting because it actually uses different addressing and word lengths depending on whether we're working with instruction memory or data memory. Remember, the AVR uses a Harvard architecture. It has completely separate paths for instruction and data memory, and so it has this flexibility. Instruction memory is divided into 16-bit words, and it uses 17-bit word addressing. So word level addressing, and the maximum, and the addresses are stored using 17 bits. And so that means the maximum memory size is 128 kilobytes, where we're using the base 2 definition of kilo, or I could say kibibytes here. But even in the AVR datasheet, you'll see that they use the prefix kilo. Data memory uses 8-bit words and 16-bit byte level addressing. And so the nice thing about the AVR processor, and also including the ARM as an alternate example, is you get a lot of experience with different types of addressing and comfort with using different types of addressing schemes as appropriate.